Hello, everyone. I am Maria De-Arteaga, Assistant Professor in the Information Risk and Operations Management Department at UT Austin. And today I'll be talking to you about 3 frontiers of responsible machine learning. Why are we talking about this? Well, in recent years, we have seen an increasingly widespread adoption of machine learning in high-stakes domains. And this has been accompanied by an increased awareness of its risks. And so in the past years, we have seen a lot of work towards responsible machine learning. And this is a good moment to think about where are we now? And so what will I be talking to you in this talk? In this talk, I'll be telling you about 3 frontiers of responsible machine learning grounded on my research. These are not all the frontiers of responsible machine learning. These are not the 3 most important frontiers of responsible machine learning. These are 3 of the frontiers. And this is primarily grounded on the research that I've done in the past years and what I've learned from it. So what are these frontiers that I'll be telling you about? First, I'll talk to you about algorithmic fairness and, in particular, residual harms of group fairness approaches. Connected to these as well, and as depicted in this graph, there's an intersection between all these topics. In the space of human-AI collaboration, I'll be talking about the gap between predictions and decisions. And finally, I'll talk about the construct gap that exists between the constructs that we care about when designing an algorithm and the constructs that we typically have access to. So to begin with, diving into the algorithmic fairness component, I'll be telling you about some work that we did with my amazing collaborators, Myra Cheng, Adam Kallai, and Lester Mackey on social norm bias. A little bit of context so that we can dive into this is many of you may be familiar with work on algorithmic group fairness. So among the different approaches that have been developed to measure and operationalize fairness-related constructs, algorithmic group fairness has emerged as the most popular approach, in large part due to its ease of application. And broadly speaking, what algorithmic group fairness does is it measures disparities across sensitive groups on a measure of interest. So for example, it may measure differences in false positive rates across racial groups. And so rather than just looking at the overall performance of an algorithm, we're looking at performance for different subgroups, measuring performance, considering different types of errors, and predict the selection rate, among many other measures that we may care about. And grounded on these measures, then there's been a lot of approaches that have been developed to enforce these constraints. And primarily, these typically fall into one of 3 buckets: pre-processing approaches, in-processing approaches, and post-processing approaches. The first one aims to transform the data, transform the input data, dropping the information that is sensitive or that we may not want to use because we consider it to be unfair to rely on that information for prediction. In-processing aims to transform the optimization objective through fairness constraints. And post-processing says, okay, we already trained one algorithm. How do we transform the output, for instance, by changing the thresholds that we use for classification for different sensitive groups? And these approaches have become very popular, and they're increasingly implemented in machine learning deployment. For instance, LinkedIn announced at one point that they were using a post-processing approach to improve the representativeness of their talent search. And it is really great to see that algorithmic fairness research is having practical impacts, that practitioners are paying attention and are incorporating these. And so where are we now? Are we done? Did we fix the problem? And the answer is, well, we're not really done. There's a lot of work ahead, right? And in particular, there's a risk when we're looking at group fairness of using reductive definitions of what membership to a sensitive group means and invisibilizing harms. One of the risks when we look at one measure of fairness is that if we think that that is capturing everything that we care about, then other forms of harms may be invisibilized. And there's been some really great work, for instance, from the philosophy perspective in this space. Here I give two examples of this work. In our research, we looked at what are some of these invisibilized harms, and we characterize what we term social norm bias, which is the association between an algorithm's predictions and adherence to social norms. And we show that this is a source of algorithmic bias that is overlooked by common group fairness approaches. Work in social psychology and organizational sciences has studied the role of adherence and deviation to stereotypes and discrimination. Madeline Haleman's work, for example, has studied prescriptive and descriptive stereotypes. In the context of gender and workplace, descriptive stereotypes refer to attributes believed to characterize women as a group. And the perceived lack of fit between feminine stereotypic attributes and male gender type jobs, so jobs that are thought to be a men's job, result in a gender bias that can impede women's careers. And so women in these fields may feel pressure to adhere to certain masculine social norms to advance their careers. And so these may present itself in pressures that we feel about the way that we should dress, the way that we should talk, the way that we should relate. And well, as an aside, deviation from descriptive stereotypes may also lead to discrimination, but we won't go into that. So the issue here, the question is, do algorithms exhibit social norm bias? Are algorithms' predictions influenced by individuals' adherence or deviation to social norms? And if this bias mitigated by group fairness approaches? There are many harms that may result from algorithms exhibiting social norm bias, and one particularly salient harm is an allocation harm. If certain individuals are allocated fewer opportunities based on their degree of adherence to social norms, such as gender norms. To study these, we conducted experiments using the task and data set bias in bios, which we proposed and collected a few years back. And here the task is to predict someone's occupation from their biography. So using this task where we want to say, well, based on this biography, what is this person's occupation? We propose an approach to measure inferred social norms, the relationship that the algorithm learns between group membership and input data. In this context, for example, this allows us to answer the question, does a biography align with what the algorithm associates to be masculine or feminine? And we show that the inferred social norms that are specific to a data set, for instance, the biography data set, reflect real-world norms and stereotypes that arise in certain settings. So based on this measure, we can study social norm bias. In this plot, what we're seeing is the percentage of people who use she as their pronouns in each occupation and the correlation between occupation and gender predictions among those who use she as their pronouns. A high correlation means that, for instance, a woman is more likely to be correctly predicted to be a surgeon if her biography adheres to what the algorithm associates to be male gender norms. And these, ideally, if there was no social norm bias, we should see that the occupations lie on a horizontal line around 0. But we see something very different. We see that the strength of correlation increases with occupations' gender imbalance. Thus, this penalizes individuals for their adherence or deviation to social norms. And this is overlooked by group fairness measures, as we see here. we see that this persists across different fairness approaches that we tested. And this is most pronounced in post-processing approaches. So when we think about it, post-processing approaches are keeping within group ordering. And so what this means is that if the algorithm has a ranking that is influenced by social norms, well, this doesn't change afterwards. And so when we apply a post-processing approach, the individuals in the disadvantaged group who are most likely to benefit from the fairness intervention are those who adhere to social norms of the majority. For instance, women whose biographies reflect a more masculine style. So what we have shown in this work is that there are invisibilized harms of group fairness. Algorithms may display social norm bias. So for example, occupation classification may be associated to individuals' adherence to social norms. And as a quick aside, I just presented you a brief overview of the results. We do a lot more analysis in which we look at what happens when we drop certain task-related relevant words and so on. So there's a lot more to this work. This is just a brief overview. But what we find is that this social norm bias is something that is not mitigated by group fairness approaches. And if we think of group fairness as the one measure that we care about, this may veil harm to individuals. And for example, it could result in fewer opportunities for people who are perceived as feminine in predominantly masculine occupations. And so the question here is, how do we mitigate these harms? And what other invisibilized harms are there? And group fairness has given us a great array of tools that are very relevant to mitigating many different types of harms. But one of the frontiers now is, how do we move past that? And how do we recognize the fact that when we're just looking at an attribute like gender as a one variable that gives us whether someone belongs to one group or not, that is reductive, and it is dropping a lot of the multidimensionality of gender and the different ways in which gender intersects with discrimination. And this happens with other sensitive attributes as well. Now moving on to the second topic, we look at human AI collaboration and the gap that exists between prediction and decisions. Here I'll be telling you a little bit about work that we presented at CHI in 2020, and we recently shared the extended version where we looked at the role of humans in the loop. And when we looking back at all of the high-stakes domains in which machine learning is being increasingly applied, we often see that both in headlines but also in research assessments, there's a major focus on predictive performance as the measure that we care about. The locus of evaluation is the algorithm. And this results in headlines such as, AI system is better than the humans, AI just beat human doctors. But often we do not care about predictions. We care about prediction-informed decisions. The reason why this matters is because adherence to predictions is not uniform and is not a given. There are, in particular, two phenomena that are of particular concern when we're thinking about algorithm-assisted decisions. And these can be thought of as two ends of a spectrum. On one end, we have algorithm aversion, which relates to undercompliance, settings in which human decision makers decide to ignore the algorithm altogether, even if the algorithm may have useful information that could improve the quality of their decisions. On the other end of the spectrum, we have automation bias. And this is a case in which the humans say, well, this algorithm is so smart, I'll just rely on it. Or there's so much time pressure that there's an incentive to just indiscriminately adhere to what the algorithm is saying. We study this in the context of child welfare. where algorithms are increasingly being used to assist call workers who work at child abuse hotlines and are tasked with deciding which calls are screened in for investigation. Some agencies are very hopeful that the use of algorithms in this domain can help mitigate the risk of false negatives, in which certain calls where the child was at risk are not screened in for investigation. But many others have expressed concern. For example, the National Coalition for Child Protection Reform published a commentary titled "Pittsburgh's Child Welfare Agency Goes Full Orwell." And understanding how humans make use of recommendations in this context is one piece of the puzzle in order to understand potential benefits and risks of using algorithms in these domains. So before the deployment of the tool, Allegheny County, which is the county where Pittsburgh is located and where we conducted the study analyzing the deployment of their tool, the way that the pipeline used to work is a call worker receives a call. They have access to historical records, which is a lot of administrative data concerning the child and adults involved in a call, and they decide whether the call is investigated, whether an investigation is open based on the information communicated in the call and the historical records. When the algorithmic tool was deployed, which was in 2016, then the call workers had access to the same information that they had before, but in addition to these, they also had access to the output of a predictive model. The predictive model was giving a risk score and a flag that indicated that a supervisor's approval was required for screen out in some cases. Importantly, the predictive model only relied on the historical records. It did not have access to the information communicated in the call, and call workers were tasked with using this information as complementary. There was a technical glitch when the tool was first deployed, and as a result, some scores were miscalculated in real time. So approximately 10% of scores were miscalculated by 5 or more points. So what we see here is the assessed score, this is the correct score that should have been shown, and the score that call workers saw. Naturally, there's a strong correlation between these two, but the fact that some scores were misestimated allowed us to study how the humans behaved when the incorrect score was shown. And here I'll just give you a brief overview of the results. There's a very, very long analysis, so I encourage you to look at the paper if you're interested in it. But as a brief overview of the things that we found, one of the most important phenomena that we identified is the fact that coworkers avoided automation bias in the forms of errors of omission. What we're seeing in this plot is the bin scores based on the assessed score and the screening rate for each of these. So correct indicates that the assessed score is equal to the shown score. Underestimation means that the score shown was lower than the assessed score, and overestimation means that the score shown was higher than the assessed score. If coworkers were indiscriminately following the score, we should see that those that the score shown was underestimated were screened in at a lower rate. Those where it was overestimated were screened in at a higher rate. So we should see a trend like this. What we see is very different. We see that actually cases with an underestimated score were screened in at higher rates. And here it's important to recall the non-random nature of the glitch. But what this means is that call workers were not just relying on the score and were using other forms of information, integrating them into their decisions. And as a result, this allowed them to avoid automation bias and avoid errors of omission. A focus on decisions rather than predictions also has implications for fairness. In some domains, such as criminal justice, it has been shown that differences in likelihood to adhere to algorithmic recommendations may exacerbate risks of algorithmic bias. In this domain, we find that humans in the loop mitigate bias with respect to the algorithm making decisions alone when measuring bias as disparities in selection rates. So here we don't have a ground truth that allows us to measure certain metrics such as false positive rates or false negative rates, because when a call is screened out, we don't observe what would have happened had an investigation been conducted. And as I will discuss in a moment, labels that are available after investigation must be understood with a lot of nuance. And so we decided to focus on selection rates. This means that a disparity, a difference in this measure, is not inherently representative of unfairness. It could be the case that there's one community that needs more resources than the other. But it still tells us about how resources are being allocated. And given that Child Protective Services investigations place a burden on families, it does tell us about how these burdens are affecting different communities. So prior to the deployment, we see that calls that involved at least one Black child were more likely to be screened in for investigation. And if the algorithm had been making autonomous decisions, which importantly, this is not something that has been considered, this just allows us to see what are the algorithmic predictions doing, and then what is the role of the human in the loop. That's why the algorithm alone as a comparison point is relevant. And what we see is that the disparities would have been exacerbated. And because both of these disparities are going in the same direction, we could worry that a human in the loop, a human and an algorithm acting together, would compound this disparity. But that is not what we see. What we see is that a human in the loop mitigated the disparity with respect to the algorithm alone. And there's two important elements when we, as I said, this is work that has a very, very thorough, very long analysis. So I encourage you to look at the details if this is something that you would like to learn more about. But to give you an overview, what we find there is humans did change the way that they made decisions when the algorithm was deployed. So this is not that humans are just falling on algorithm aversion, ignoring the algorithm. And we also showed that it's not because humans' adherence to recommendations depends on the child's race. Rather, as we discussed previously, because humans integrate other sources of information, such as the information communicated in the call, this means that they're not just screening in the highest scoring cases. And relying on other sources of information and other signals changes the mixture of the cases that are screened in for investigation. And so what is very important to take from this is the fact that predictions are different from decisions. And it is really important that as we start designing for human AI collaboration, for algorithmic decision support, we must center decisions as the locus of evaluation. And how humans make use of recommendations matters and varies. Here I showed you a case in which the co-workers were avoiding errors of omission, for example. There's other work that has shown evidence of automation bias in some domains. And so algorithm aversion and automation bias are real, but that does not mean that humans always make poor use of algorithmic tools. And so the key question here is, how do we design for productive human AI collaboration? And finally, very related to this, we get to the third frontier, that is bridging the construct gap. And what I will be telling you about briefly is work from our paper, leveraging expert consistency to improve algorithmic decision support. So when we're centering decisions, the construct that we care about is typically complex, multifaceted, and sometimes even contested. In healthcare, we may care about patients' healthcare needs. In hiring, we may care about prospective employees' potential. In the child welfare domain, we care about, is the child at risk? But what we're optimizing for in an algorithm is a quantifiable and imperfect proxy. We may only be able to measure healthcare spending or whether someone got a job promotion. In the child welfare context, the observed outcome is what is the probability of out-of-home placement, whether following an investigation, the child is placed out of the home, which is what is typically known as foster care. And it is really important to mind the construct gap. So in the child welfare domain, when we look at what happens when we train a model to predict out-of-home placements, this is what we're seeing in green, and we look at what happens when we train a model to predict the human decisions. And we measure their performance with respect to out-of-home placement. What we see here is that the model that was trained to predict the observed outcome rather than the human decisions is doing a lot better. But there are other outcomes of interest. The only thing that we care about is not whether there's an out-of-home placement. There are many other cases in which, for instance, services are offered to the family, the risk to the child may be reduced, and there's no need for a family separation, which these are very important cases to identify as well. And so we can think of these as unobserved outcomes. It could be the case that there's enough correlation between the cases that result in out-of-home placement and the cases that have other unobserved outcomes of interest, so that predicting just out-of-home placement is fine. But that is not what we see. What we see is that when we look at these unobserved outcomes, then the performance of the model that is trained to predict out-of-home placement drops significantly. And the performance of the humans is significantly better. And so what we see here is that there are elements that humans are optimizing for that are relevant and that are not captured in the observed outcome that is used to train predictive models. And so the question is, where do we go from here? How do we optimize for what matters? In our work, we tackle this problem by saying, can we learn from experts' decisions when they display certainty and consistency, and learn from observed outcomes otherwise? I won't go into the methodology that we developed to be able to do this, but what we find is that there are pathways, and the method that we propose is one such pathway to bridge the construct gap by combining observed outcomes and human decisions. And so here you're seeing the methods that we're proposing. You can see how they retain performance with respect to the observed outcome, that is a central outcome of interest, but they still perform well with respect to other outcomes. And so they're kind of giving us the best of both worlds. And so here it is central to remember that the measured construct is not necessarily the same as the relevant construct. And when we evaluate with respect to the measured construct, this may also be misleading, and it may invisibilize some ways in which the algorithm is failing to optimize for the things that we care about. And so the question is, how do we bridge the construct gap? We've proposed one such approach, but this is just a first step in what I believe to be a very deep area of research. And with this, I will finish for today, and I am very much looking forward to your questions. Thank you very much.
Maria De-Arteaga, this was a wonderful presentation. My question is, for your future work, what are you thinking are the challenges that you're going to face, and what are the different applications that you're going to focus first?
Yeah, thanks for your question, and thanks everyone for joining for the talk. I think that one of the elements that I'm most interested in right now is there's very clear from the empirical results that we have that when we're using machine learning to support experts, things can go really well, but they can also really fail. And so algorithm aversion, automation bias, we have a lot of evidence showing that that may happen when we deploy systems, but we also have evidence like the one that I discussed showing that humans can have a productive role in a human-in-the-loop system. And so I think that one of the most exciting areas of research is how do we design, both when we think about the socio-technical system, but also when we start thinking about designing algorithms that are purposefully designed for decision support and not for automation, that leads to that productive human AI teaming. And so I think that that's where we have a lot of unanswered questions. That is, how do we design then being able to anticipate that we'll get these productive collaboration.
Perfect, thank you. We have maybe more questions?
Hi, thanks for the talk. One problem with these outcomes of biased outcomes of models, it comes from the data itself. You know, as you said, like there's when you associate some specific targets, the data itself it's already biased towards something. For example, gender, etc. So, is there any other way that you believe it would be possible to reduce it without humans in the loop, or do you believe that that's really necessary? I mean, automatically.
Yeah, so I definitely think that there's ways in which we can design bias mitigation strategies that are very productive, and while they're not the whole solution to the problem, I think that they're an important part of the solution. And one of the things that we show in the first version in what I discussed in the first portion of the talk on social norm bias is that there's actually really big differences in how different approaches mitigate these bias or fail to do so, right? And so I think that in the context of that work, for instance, one of the takeaways is when we're looking at post-processing approaches, for example, which are very attractive in terms of not requiring retraining, and along other dimensions, we now see a clear trade-off with these type of bias mitigation, whereas we see that other approaches that are, in particular, in-processing approaches, that basically what they're doing is they're nudging the model to not focus on certain signals, and so that does mitigate the social norm bias. So I definitely think that bias mitigation strategies can pan out very differently, and I think that there's a lot of work there in terms of different approaches that don't rely simply on binary or just categorical protected attributes. So in work that we presented at NACL a couple of years ago, we looked at how do you mitigate bias when you don't have access to protected attributes, but you have access, for example, to names, and then you can leverage the fact that word embeddings encode information around what those biases could be. And so it's a fighting bias with bias type of approach. And so I think that there's a lot of avenues for exploration. And while human AI collaboration, human in the loop are important, I definitely think that algorithmic driven approaches are an important piece of the puzzle to mitigate bias in an overall system.
Perfect, thank you. We have more questions? Okay, thank you, Maria Arteaga, for your time.
Thank you, everyone.